guys, this week we will continue discussing good properties of estimators. We start with a consistent estimator. This is about the variation of the estimators actually. We want the estimators or statistics have small variances. Then we know that they converge to their expectations very easily, or when we have a sample, if the variance is small, this means that the observed sample will give me consistent results actually. So our first today we will start with consistent estimators. This consistency related with the variance of the estimators. So consistent estimators. We will use CE notation for consistent estimators this semester. Next semester we will use CE for confidence intervals or confidence intervals. Okay. Actually, we will use CI notation, not CE. Okay. So let's consider the definition of that. So we have an estimator, theta hat, which converges in probability. I hope you remember these convergence rules or the meaning of convergence in probability to an unknown parameter theta for all theta values in the parameter space is called a consistent estimator of theta. So this means that theta hat is a consistent estimator if and only if it converges in probability to theta. Okay. MLEs are generally consistent estimators. Okay, so basically we are using in convergence in probability case we are using Chebyshev's inequality, if you remember. We are looking at the probability that the difference between theta hat minus theta in absolute value is less than the variance of the theta hat over n. So if this is the case, or the epsilon, I think, so epsilon square. If you want, you can use this actually, but we have a different approaches. Sometimes we are using vehicle of large numbers, if you remember. So expectation of an estimator converts to if the expectation of the estimator equals to the parameter, then basically we can use vehicle of large numbers. In that we have three rules, if you remember. Actually we are using Chebyshev's inequality, but if you check, or let me say by Chebyshev's inequality, if the estimator satisfies these two rules, if theta hat is an unbiased estimator of theta, or theta hat is an asymptotically unbiased estimator of theta. Okay, this is one rule. The variance of theta hat should be finite for all theta values in the parameter space. The third rule, limit when n goes to infinity, variance of theta hat should be 0. Okay. So if these three conditions are satisfied, all of them together, then we can say that theta hat converges in probability to theta. And in that case, basically theta hat will be a consistent estimator of theta. Okay, so basically you have to check these three conditions. Let's look at some examples. So consider, so let's say we have a random sample first. And we want to show that sample mean x bar consistent estimator or not for the population mean. So consider x bar. So we want to show this. Basically, this is true by weak law of large number. So by weak law of large number, x bar converges in probability to mu. So this means that x bar is a consistent estimator of mu. But let's check the rules also. The first one, expected x bar always equals to the population mean. The first rule first condition satisfied. Then the variance of x bar is sigma square over n, whatever that is. So it is finite. And third rule, limit when n goes to infinity, variance of x bar, limit when n goes to infinity, sigma square over n is 0. So all these three conditions are satisfied. Then we can say that x bar converges in probability to mu. So x bar is a consistent estimator of mu. Okay. Similarly, we can do the same thing for, this is true for any distribution, any distribution. So consider s square, summation xi minus x bar whole square divided by n minus 1. So we know that expected s square is sigma square. For any distribution, we focus on normal distribution, but this is true for all distributions. So this means that s square is an unbiased estimator of mu. So first condition satisfied. And for many distributions, so we have to know specific distribution to show that, but this is true for many distributions, most populations, true for the most populations. So s square is also a consistent estimator of sigma square, not mu. Okay, sigma square. So let's consider another example based on the okay, so let me see this another example. Let me show you. Okay, so this is an unbiased. These are about the unbiasedness. Okay, so let's consider a binomial case. So let's say we have binomially distributed random variables with success probability p, and we have a random sample of size n. So let's say is the MLE of p consistent estimator of p. Okay, so this is our question. So let's first find the MLE of p. So let's write the likelihood function. For this one, we already know actually the MLE. Okay, so this is the range for p, p summation xi ln p n minus summation xi ln 1 minus p. When you take the derivative of the log likelihood function equated to 0, you get p hat as x bar. Okay, and you have to check also the second derivative. Okay, so this is the MLE. So let's consider the consistency. Okay, so first of all, first condition is expected p hat. Expected p hat equals to expected x bar equals to p. So we already know that this condition satisfied. The second one, variance of p hat, variance of x bar. For binomial, what is that? P 1 minus p over n. So it is finite for all p values in this parameter space 0, 1. The third condition, limit when n goes to infinity, variance of p hat equals to 0. So this condition also satisfied. So this means that p hat converges in probability to p. We have lots of p's here. Okay, so this also means that by definition p hat x bar is a consistent estimator of p. So we are saying A because consistent estimators are not unique. So we can have more than one consistent estimator for unknown parameter p. Okay. So what else? We have, let's say for normal distribution, x normal distributed with mean, mu, and variance sigma square. So here the question is find the MLE of mu square and check whether it is a consistent estimator, and check whether it is a consistent estimator of mu square. So this is the question. So first find, actually we know the MLE of mu, right? It is x bar. So by the invariance property, mu hat square x bar square is the MLE of mu square. Okay, so the first one is done. So let's check the consistency. So to be able to show the consistency, we have to find the expectation of x bar square, and we need to show that it converges to mu, or it is mu square actually, and the variance of x bar square goes to 0. Okay, so here expected x bar square. So this is variance of x bar plus expected x bar whole square. Okay, definition of expected squares. So we have sigma square over n plus mu square. So this is not exactly mu square. So x bar square is not an unbiased estimator of mu square. But when we check the expected x bar square converges to mu square as n goes to infinity. So this means that x bar square is an asymptotically unbiased estimator of mu square. So this condition satisfied. Then actually I didn't calculate the variance, but we can say that variance of x bar square is expected x bar to the 4, so you have to find this x bar square finite, and actually we know that it is a function of sigma square over n, and here it will be also a function of some value over n, so it is finite, but it converges to 0 as n goes to infinity. So you can calculate expected x bar to the 4 and then calculate get the exact value. So these conditions are also satisfied. This means that x bar square converges in probability to mu square. So by definition, this means that x bar square is a consistent estimator of mu square. So I have solved the question actually. Okay. So we have another topic. It's actually very important, which is mean square error and mean square error consistency. So mean square error is very important actually in many cases nowadays, actually also in data science and machine learning algorithms we are using mean square error a lot. So we will see theoretical calculation of the mean square error, but actually it is a difference between the original parameter value and the estimator, difference between original parameter value and the estimated in expectation. So if you want to show if you want to show our estimator is correct, or if our predictions are correct in using some certain modeling tool, then what we are doing, obtain the predictions, obtain the original values, get the difference between them, square differences, get the average of the square differences actually. So mean square error is a good tool that your prediction model is also good, or your estimator is good or not. Okay, so mean squared error. So it's an important tool. We have the root mean square error also. So here we are using the theoretical based mean square error. The mean square error of theta hat is defined by, so mean square error of theta hat to estimate theta. It is the squared differences between the estimator and the unknown parameter. So when you open this up actually, so you will see that, let's open this equation. So we have a shortcut formula. So expected theta hat minus theta, get the square. So expected theta hat. Let's add and subtract the expected theta terms here. Oops, I already put a minus sign. Okay, expected theta minus theta whole square. Okay, then get expected theta hat minus expected theta whole square plus expected theta minus theta whole square. Theta hat, sorry, these should be theta hat. And also add plus 2 times expectation of theta hat minus expected theta hat and expectation of expected theta hat minus theta. Okay, so when we took this actually, so here expected theta hat, so this quantity will be 0. As you can see, expected theta hat minus expected theta hat, expected, so this part, expected theta hat minus expected theta hat, it becomes, so it will be 0. So expected theta hat minus theta whole square can be written as, so as you can see here, this part is the variance of theta hat, right? Plus this calculation is bias. Okay, so what we have here is bias of theta hat theta whole square. Okay, so what we have here is mean square error of theta hat minus theta for estimating theta equals to expected theta hat minus theta whole square. But when we have the estimators, basically this is much more easier. So we have the variance of theta hat plus the bias square. If you have an unbiased estimator, then this part will be 0. So mean square error. So if theta hat is an unbiased estimator of theta, then the bias term will be 0, and in that case basically mean square error theta hat to estimate theta will be just the variance of theta hat for an unbiased estimator. Okay, so how we can use using these mean squares? So let's say we have 2 estimators or more than 1 estimator to be able to estimate an unknown parameter theta. So if mean square error, oh sorry, before that let me if we have okay, if let's say theta 1 hat and theta 2 hat are estimators. Let's say one of them is MLE, one of them is MME, estimators of theta. So to be able to compare, these estimators, we are using mean square errors. So we are calculating the mean square errors. Calculate mean square error for theta 1 hat to estimate same theta. Get the mean square error for theta 2 theta. Okay, so let's say mean square error for theta 2 is bigger than the other one. So this means that the variation, both bias term and the variation, is smaller in the theta 1 hat case. So we have to prefer theta 1 hat over the theta 2 hat. So theta 1 hat is a better estimator of theta compared to theta 2 hat. Because mean square error formula, if you remember, it is variance plus the bias square. So variation is low, this is good. Bias is small, it's also good. So we have to prefer the one with a smaller mean square error. So this is our comparison tool. This is not the best estimator, it's a better estimator. And here, if we have several estimators, basically we can compare them and we can find a better estimator among the others. So this is not the best estimator. So let's consider a simple example. Okay, so let's say we have just 3 random variables. Be a random sample of size n equals to 3. Actually, let me stop now and then I will continue in the next video.